All right, it's 2 o'clock, so we can get started. Welcome, everyone. Thank you for attending our first iteration of the Third Coast Water Seminar Series. Today, we will be hearing from Dr. Ali Ling about a practical guide to PFAS remediation. To kick off our series. But before we get into that, a little bit of backstory. So my name is Tyler Steven. I am the technical program manager with Current as well as this Third Coast Water Seminar Series is focused around this concept of transforming waste into wealth. Current was founded in 2016. And is focused on growing the circular blue economy, accelerating water innovation, and solving pressing water challenges. We've kind of think of ourselves as conveners and facilitators. We have engaged with various different communities, including researchers, industry folks, entrepreneurs and startups, as well as direct community involvement and engagement. To really solve pressing water challenges, drive economic opportunity, protect public and environmental health, and safeguard our nation's most critical asset, which is our fresh water. Since our founding in 2016, we have engaged over 40 startups, piloted over a dozen technologies, raised over $58 million, and engaged over 40,000 people through various events, convenings, and training programs, which all led to us being able to anchor the NSF-funded Great Lakes Innovation Engine, Renew. The Renew part stands for the recovery of energy, nutrients, critical elements, and water. And so really the focus behind this innovation engine, which is setting us up for up to $160 million over a 10-year period, is focusing on the Great Lakes region, initially Illinois, Ohio, and Wisconsin, and eventually expanding to include Michigan, Indiana, and Minnesota. So our key objectives through Great Lakes Renew is to spur the circular economy transition, so focusing on ecosystem building and workforce development surrounding the circular blue economy, facilitating and supporting the invention and commercialization of selective separation technologies, focusing on those key elements of critical minerals, water, energy, and nutrients, as well as attracting and retaining water-intensive industries in the Great Lakes region. And through this effort, we have several research and development priorities that we are funding and supporting. We are supporting cutting-edge breakthroughs around PFAS detection, sensors, critical mineral extraction, nutrient recovery, wet weather treatment, and more. And if you want to learn more about us, you can go to our website. You can join our email list, follow us on social media. We would love to keep you all engaged in our efforts. But to get to the crux of it, I'm going to pass it over to Dr. Melissa Pierce, who's going to introduce our speaker for today.
Thank you, Tyler, and thank you to everyone for joining today. We're so excited to have everyone here to kick off our inaugural relaunch of this seminar series. And today we're starting with Dr. Ali Ling. So Ali's career has focused on using basic science concepts from environmental chemistry and microbiology to solve engineering problems. Her research work aims to inform technical and regulatory decision-making by using systems thinking to understand technical, economic, and social impacts of environmental engineering technologies. During 9 years in consulting, Ali addressed and developed water and wastewater treatment solutions for clients across municipal, mining, and manufacturing sectors. Dr. Ling has shared insights about environmental issues across multiple media, including textbooks, podcasts, and public speaking engagements. She's a registered professional engineer in Minnesota and a member of the Water Environment Federation and the American Waterworks Association. She's also a board member of Freshwater, a Minnesota nonprofit focused on empowering people to value and preserve water. So Dr. Ling received her undergraduate degree in civil engineering from the University of Minnesota Twin Cities. And she also has a master's and a PhD from the University of Colorado at Boulder, also both in civil engineering. On a personal note, I highly recommend after this, everyone go follow Allie on LinkedIn. She's always sharing really insightful commentary and thought leadership on PFAS solutions and new research. So a little plug for following her there. I always enjoy her content. So that's Allie, and go ahead and take it away.
Thanks, Melissa. All right. So the title of my talk is A Practical Guide to PFAS Remediation, but we're kind of going to take a little trip here. We're going to zoom out a lot and think about PFAS in the environment as a whole and kind of what we know about costs and implications and what we can do about it. We'll talk a little bit about PFAS remediation and kind of a framework for thinking about decision making there. And then I'll talk about a specific case study where we applied that framework. And then you'll get a little sneak peek into some of the other stuff that I'm working on these days. So the thing that makes PFAS mostly different from other chemicals we've dealt with in the past is that it's persistent. It's very hard to break down, and we don't know of any natural ways that that happens in the environment where they turn into something that's not PFAS. So the problem with persistence is that if we think about the global PFAS stocks in the environment, if we have ongoing emissions, the amount of PFAS out there just increases. It's just there's a consistently increasing mass stocks, consistently increasing concentrations in environmental media. And this leads to increased potential over time to exceed both known and unknown thresholds to impact human and environmental health. So if we have something like this that doesn't degrade in the environment, we keep putting it there, like there's increasing risks, and it becomes more and more irreversible as we do it. Now, this wouldn't be a problem if we didn't make them anymore, but we still make a lot of them. So still, the current estimate is about 1,000 tons per year of perfluoroalkyl acids, PFAS. That's kind of the family of PFAS we hear most about, and up to 1 million tons per year of total PFAS. If we think about PFAS in the environment as water in a bathtub, we're filling it up with a fire hose. So if we wanted to drain that tub, we need to have active treatment and destruction. It needs to be engineered solutions because there's not natural ways to turn PFAS into not PFAS. And the cost for that is typically in the millions of dollars per kilogram or pound of PFAS removed and destroyed. And that's some work that I did, kind of just pulling stuff together. And then the next thing I did was trying to figure out if we wanted to keep the level in this tub steady such that it's not currently overflowing, how much would it cost to increase the drain, increase the active treatment and destruction to match how much we're emitting right now? And the takeaway there is that increasing remediation rates to match current emission rates would cost more than the global GDP every year. So this is a paper that I put out last year, and the takeaway here is that there's not enough money in the world to remove PFAS from the environment as fast as we're adding it right now. I feel like in the world of PFAS, we hear a lot about technologies to remediate PFAS and remove them from the environment, which is great and helpful, but that can't be the only way we get about it. So if we think about managing environmental PFAS, the priorities need to be, first, we need to reduce PFAS use. We need to be using it and emitting less of it. We can do that through use restrictions. So there's legislation in many US states. There's ongoing work on this in Europe, where there's restrictions to how many and what types of PFAS can be used in what types of products. So use restrictions, and then due diligence by companies, where companies are auditing their supply chain, understanding where PFAS in their products come from, and then working to try to reduce those PFAS in their products and manufacturing processes. So that's the number one priority. There are still places where we will need to continue to use PFAS, at least for a while. And so we need to be reducing PFAS emissions from those remaining point sources. So those are things like industrial wastewaters, landfill leachates, air emission control, especially from PFAS manufacturing facilities, and soil source control, really targeting the concentrated spots to be most effective here. And then the third priority is targeted remediation in places where there is a public health reason to do so. And the reason I put these in this order is partly because of the cost. So for targeted remediation, as I just mentioned, it's millions of dollars per pound of PFAS, and that's often paid by ratepayers, whether that's wastewater treatment, drinking water treatment, kind of general cleanup by the government. Sometimes there's lawsuits that can cover this from actual polluters, but not always. If we wanted to reduce PFAS emissions from industrial wastewaters, landfill leachates, that's typically more in the tens to thousands of dollars per pounds of PFAS, so cheaper by a factor of like 1,000. And that would get paid by industries that are, hopefully industries that are emitting those. And then costs for reducing PFAS use are not necessarily publicized. There's not a lot of incentives for companies to publicize these. There's some work being done in the EU to understand these, but I think they're going to be less than $1 million per pound. So the takeaway here is we do need remediation to solve environmental PFAS, but we cannot rely on remediation alone. Reducing PFAS use and emissions will have a greater benefit on current and future human health and on the massive PFAS in the environment. We're not going to be able to drain that tub at the rate that we're emitting PFAS right now. Let me talk briefly about health so you can kind of see what that looks like. So there's a lot of talk about PFAS in drinking water and how remediating PFAS is something we need to do to address health. And it partly is, but it's not everything. So this figure shows on the x-axis is a bunch of studies that were reviewed in this 2021 review article. And the y-axis is the percent of PFOA exposure from different sources. And the blue bars here show the percent that is from the diet, from food that people eat. The green bars show percent from inhaling dust, and the orange bars show percent from water. There's a variation in how these studies kind of measured and differentiated different things, but generally, less than 20% of PFAS exposures in the US come from drinking water. 80% or more come from other sources. This is very dependent, of course, on like where you are specifically and what you do, but generally more than 80% is from other sources dominated by food and dust that we're breathing. So my takeaway there is, if we're thinking about remediating the environment, okay, if we even could remediate everything in the environment, which we know now is logistically and financially impossible, we could get the drinking water. We might be able to get some environmental inputs to food from, soil and grain and stuff. But a lot of that food PFAS might come from food contact materials. It might come from manufacturing and processing. Generally, remediation is really only going to address about half of current exposures. The rest are through products. So even if we could remediate everything, we still would only be addressing about half of PFAS exposures. So that really, to me, really highlights the need to focus on PFAS and products, PFAS uses and emissions. Okay, so now that we've got the big picture, we're going to see how remediation fits in. I'll talk a little bit about remediation and what sorts of questions we should be asking to do a remediation project right for PFAS treatment. So I'm an engineer, and we're trained to do the project right. The thing that we're not necessarily trained as well to do is to do the right project and really prioritize what sorts of projects and efforts are the most important and the most beneficial for public health. And that's not necessarily the job of some engineer who's the boots on the ground or the designer for a specific project. It's more in the context of public policy and lawmaking. But we're just going to talk a little bit about this. On the remediation, I'm going to go through 5 different questions that I think everyone should ask about specific remediation projects in order to come up with a successful approach for PFAS remediation. The first question is, what is your metric for success? This isn't going to be the same for every project. Sometimes the goal is to reduce the health risks. So if we're looking at drinking water treatment, or if we're looking at managing some contaminated soil that's in a park where kids are playing, it might be to reduce immediate human health risks. But in other cases, the goal might be to reduce the environmental PFAS stocks. Maybe there's an aquifer or a soil or a surface water where there's not necessarily a human that's intaking that or going to have risks from that. So those are kind of some of the different goals. The measurable benefit from that is if we're trying to reduce health risks, the measurable benefit is like a unit of risk reduction. And if we're trying to reduce environmental stocks of PFAS, the measurable benefit is PFAS that's removed and destroyed from that. Because if we don't destroy it, it can just get back into the environment. So going under the assumption that there is limited funding for PFAS remediation, success metrics that we can use here from a kind of a policy and prioritization standpoint is how much does it cost per unit risk reduction and how much does it cost per mass of PFAS removed and destroyed. So I mentioned this cost per mass PFAS removed and destroyed metric earlier. I'm going to go into a little bit more detail about it. So this is for my paper last year. I reviewed some studies and some actually built projects and came up with this relationship. So the x-axis here is the PFAS concentration in environmental media in parts per trillion. And you can see on the left is more diluted with drinking water, on the right is more concentrated with leachate and biosolids. And then the y-axis here is environmental remediation costs in those units of money per mass of PFAS removed and destroyed. And you can see there's a very clear relationship here where it costs more per mass if it is more dilute. And intuitively, this makes sense because if you've got something that's really diluted, not a lot of PFAS in there, you're going to have to treat a lot more volume of that water or that soil to get to a certain amount of PFAS. If it's a lot more concentrated, like it is in landfill leachate and biosolids, you don't have to treat as much of the volume to get to a certain amount of PFAS in there. So the takeaway here is that if we're looking at managing emissions, we should be targeting concentrated streams. So some places where it doesn't really necessarily make sense to manage emissions are places like ambient air emissions, like municipal wastewater treatment emissions. Places where it might make more sense are, incinerator, stack gases, contaminated soils with exposure potentials, biosolids on agricultural fields, or discharges from commercial users. But the places that really make the most sense to treat for PFAS in terms of a cost per mass, and we saw this when we were talking about, tens of dollars per pound versus millions of dollars per pound, is landfill leachate and air emissions and water emissions from PFAS manufacturers and PFAS users. So that's kind of going upstream as far as you can to those concentrated sources is going to get the most bang for your buck. So that's kind of on the what metric are you targeting? The second question I want to ask about projects is what is the final PFAS fate you are targeting? I rank this on a scale of 0 to 3. So a scale of 0 PFAS fate means that the PFAS is not destroyed. It re-enters the environment within a year or so after disposal. So an example here is you might have drinking water, you're treating it with reverse osmosis, and you send that brine concentrate directly back to the ocean or to a river. So in that case, you are mitigating the immediate public health risk of that drinking water, but that PFAS, you're not removing it from the environment. It's just going right back into the environment. Level 1 is the PFAS isn't destroyed, but it's sequestered for like years to centuries. So this is things like landfills, where it would get re-released. A lot of it comes out through landfill gas, and some of it comes out through the leachate as well. Deep injection wells, which is a disposal method for some industrial wastewaters, and then some in situ treatment just sequesters it rather than destroying it as well. And then once we get into kind of level 2 and 3 of the PFAS fate, this is really where we want to be if we're trying to manage the stocks of environmental PFAS. Either some PFAS destroyed or near full mineralization. So mineralization means breaking all the carbon-fluorine bonds and it's not a PFAS anymore. There's a little bit of like analytical uncertainty and other method things that make it challenging to figure out, is something a 2 or a 3, especially if there is a stack gas because it's hard to measure PFAS in air. But really we should be, if we're looking at managing environmental PFAS targeting 2 and 3, I sometimes see people comparing costs or outcomes from 2 different projects, and one of them might be a 0 and one of them is a 2. And it doesn't make sense to compare costs about those 2 things because the things that you're buying are very different. You're buying, reducing health risks but not destroying the PFAS, or you're buying reducing health risks and also destroying the PFAS. So thinking about those 2 and 3 levels, like what are the PFAS destruction technologies that we have available? As I mentioned, the thing that makes PFAS really kind of extra challenging is its persistence. Those carbon-fluorine bonds are very strong. It's really hard for chemicals and other things to get in there and break them apart. This graph kind of shows the what types of energy that you can add to destroy PFAS. So if you are just adding heat, you can destroy PFAS through high temperature incineration, usually at hazardous waste incinerators, or regenerative thermal oxidizers is kind of the technology to remove it from air streams typically. So this is kind of liquid and solids and air streams. These are both readily available, commercially relevant technologies that are used. Again, whether it's a 2 or 3, there's still uncertainty and debate about that, but there's PFAS destruction happening here. There are other emerging technologies that are at various stages of technology readiness, but hydrothermal alkaline treatment, HALT, and supercritical water oxidation, SCWO. I love these cute acronyms, but they use some combination of heat and pressure and sometimes chemistry to destroy PFAS as well. And then there are some technologies that work at ambient temperature. So there's not necessarily heat added, but they're adding electricity, chemicals, UV light, and something other stuff that's working. So there's a lot of really great research and scale-up work being done in this area. I think there's likely to be space for multiple technologies, and the feasibility is going to depend on application. Some of these work better for solids versus liquids. Some of them work better for salty water or not salty water. Some of them only work on clear water and not cloudy water. So there's a lot of project-specific considerations that affect which ones of these might be most effective. And there's also some variability in the technology readiness for them. Okay, so now we've talked about your metrics and the PFAS fate. Let's get into doing the project right. So I find that in talking about emerging contaminants, we also often see people taking a technology-centric approach where someone's got this tool or a hammer and they're looking for something to use it on. I think it's very important to think from a project-centric approach. So what is the problem? What is the project that we're actually trying to apply here to solve? And then use that to try to understand what approach is. And then once you've got the approach, then you select the technologies. So let's get back to my list of questions. The third question here is, what phase are you treating? Often when you have PFAS treatment systems, you're going to have 2 separate steps. You're going to start with water or soil that has PFAS in it or on it. And then you're going to have a PFAS separation or concentration step so that you've got clean water or soil with minimal PFAS on it. And then you've got soil or water with a concentrated PFAS on it that goes to the PFAS destruction or disposal step. Because PFAS are often present at very low concentrations and can be very dilute, this concentration separation step is really important, that you're not paying for PFAS disposal, PFAS destruction on like a huge volume of material. So the phase you're treating is really going to affect the selection of that PFAS separation and concentration technology. So here's some of those technologies. There's liquid to solid separations like this on the top left. We've got granular media treatment, so things like GAC, adsorption, ion exchange. There's a bunch of other great adsorbents that are coming online specifically for PFAS. But this is where you take PFAS in a water phase and then you stick it onto a solid phase, and the volume is going to be a lot smaller, and then you've got a solid phase to manage. This is going to be very common at drinking water facilities as people come to comply with the current federal requirements. Solid to liquid separation, this is usually applied for contaminated soils, and it's often the current kind of method right now is soil washing, which is like a fancy way to wash soil with soapy water. And then you take the soapy water and then you treat that water with one of these liquid options. There's work being done here, but that's kind of the way that people are often taking PFAS off of soil. And then the liquid to liquid separation, I think, is a very interesting area. You've probably heard of nanofiltration and reverse osmosis membrane separation, where you've got a brine that's going to retain your PFAS. There's also on-site media regeneration. People might not usually think of this as a liquid to liquid technology, but really you're treating a liquid, and then what you end up with is a spent regenerant liquid. So it is really kind of a liquid to liquid concentration step. And then foam fractionation is getting to be more popular, and it's very PFAS specific. So PFAS are surfactants, which means they stick to surfaces of, between water and air. So like bubbles. So in this case, foam fractionation, they put a bunch of fancy bubbles in there at various, sizes or gas types that might differ. You might add some surfactants too, but what you end up with is you've got treated water, and then you have this foamate that has the PFAS in it. I'll talk a little bit more about these 3 in a minute. So the fourth question is which PFAS are you targeting? And this makes a big difference because different technologies are more effective for different types of PFAS. So some of the nuances here are the chain length, which is kind of how big it is. Does it stick to solids, or does it stay in the water? The family, in terms of the other chemistry stuff, how do you measure it? Is it measurable? What labs do you use? So these are some of the questions we should answer. It is complicated by the fact that there are a lot of PFAS. The technical number is, thousands of PFAS, tens of thousands of PFAS out there, but there really are only about 250 that are commercially relevant right now that companies are actually making and selling. And so, I don't think it's impossible that we'll be able to measure most of the important PFAS, in the next 5 or 10 years. But there are a lot of them. So this shows kind of the difference in chain length and the difference in cost. So this is from a study that I worked on when I was with Bar Engineering in 2023, and looking at removing PFAS from wastewaters or landfill leachate. So if we're going to target the 4 carbon instead of the 8 carbon PFAS, the cost is typically 1 to 2 times as much. If you're going to go and target the 2 carbon PFAS, TFA, which is in fact the smallest PFAS there is, that could be more like 2 to 4 times the cost of treating PFOA or PFOS, and that it might be even more as we get to learn more about some of this. So the PFAS that you're targeting is going to affect the costs, and it's going to affect the technology selection. So here's one example of that. I've got these 3 liquid-to-liquid separation technologies. And the ones on the left, it's kind of in order of better short chain removal. So if you need to remove the short chain ones, membrane separation is going to work quite a bit better than foam fractionation at this stage. But it's an opposite direction for better concentration factors, which usually scales with cost. So NF and RO membrane separation, depending on what water you start with, you might end up with 1% to 10% of your original volume as that concentrate. And if you're treating millions of gallons per day, that's a lot of concentrated water that you still need to deal with. On-site media regeneration is kind of in the tens of thousands concentration factors. So you go from 10,000 volume in, and you might have 1 to 10 volumes out. And foam fractionation is kind of on the thousands to millions. So if you've got 100,000 gallons in, you might have 1 to 10 gallons coming out in the foamate. So there's definitely trade-offs in this. The last question I want to ask here is what else is in there? So this is especially relevant for water quality. This table shows some different types of water you might want to be treating for PFAS, along with a PFAS type, other types of stuff in there. And this is really going to affect the pre-treatment for PFAS treatment. So if we look at landfill leachate, industrial wastewaters, municipal wastewaters, and surface waters, typically those are not necessarily clean enough to go directly into RO, GAC, or anion exchange resins. So you need to have some sort of a pre-treatment that's going to remove organics, it's going to remove solids before it gets there. And in some cases, that pre-treatment can be more expensive or more complicated than the PFAS treatment itself. So it's really important to understand what else is in there and what sorts of pre-treatment you need. So I'm going to go through a couple case studies here. This one is these map with the questions. So on the left, you see the success metric, PFAS phase, which PFAS, and what else is in there. Here's an example where you might have some leachate you're treating, and you want to sequester it. You don't need to destroy the PFAS. In this case, we're treating legacy precursors, so long chain PFAS, and we're treating high PFAS and organics. So foam fractionation is a good option here because you don't need pretreatment to treat a complex waste stream, and it's good at treating some of those legacy precursors, those long chain PFAS. So you could use foam fractionation. You could just send the foamate back to the landfill, which some people are doing. If you wanted to destroy it, if we added that in, you could send that foamate to a liquid destruction step instead. So leachate is a pretty good application for foam fractionation, but it depends on which PFAS you're treating, of course. Here's another example that's an industrial wastewater where they're trying to destroy the PFAS, and they've got short and ultra short PFAS in there. So foam fractionation and GAC are probably not going to work very well. The water is also very salty with high PFAS, so you probably wouldn't want to put it through an RO membrane. So in this case, you could use something like regenerable ion exchange, which would stick the PFAS, and then you'd have the spent regenerant that you could send to liquid destruction. A third case study here would be kind of groundwater remediation, and you might be trying to sequester it. So it might be, maybe it's an aquifer where there's not an immediate downstream receptor like a drinking water well. So we might be trying to just sequester it, or it's not, what happens in the future is less important than what's happening now. So you can use something here called the colloidal activated carbon barrier. So this would be in situ treatment. It would be like step 1 on the fate, where you're not actually destroying it, you're just kind of sequestering it for a while. But in some cases, this might be a good option. So those are kind of the questions and considerations for remediation. I want to talk about this one study that we recently completed. We presented this first at WEFTEC last year in 2024, and then it just got published in Water Environment Research. It is open source, so if anyone wants to look at it, but we're trying to understand kind of what to do with spent media management. And this was a collaborative effort, so I led it from the University of St. Thomas. We worked with 4 PFAS technology vendors, 374 Water, ECT2, Revive Environmental, and Aquaga. And then we also worked with some folks at Bar Engineering, which is a consultancy out of Minneapolis, and the Colorado School of Mines. So briefly talking about why spent media management is important. This is a figure that I show a lot, but this is kind of the urban water cycle. So we've got water in groundwater or surface water. We treat it for drinking water, potable water supply. We use it in our homes and businesses. It gets sent to municipal wastewater treatment, sometimes with an industrial pretreatment step, and then the treated effluent goes back into the water. So this is kind of how we use water in our society. Some pinch points for PFAS coming up here are drinking water MCLs, which were published in the U.S. last year. There's still some uncertainty regarding, when they'll be in place, but very likely to happen. And then wastewater permitting, this is a little bit more uncertain, and hopefully we don't do a lot of treating PFAS at wastewater effluents because it's really costly and really challenging, but hopefully that leads to permitting and removing PFAS upstream at industrial facilities. So the takeaway from this is all of these regulatory pressures are going to drive more spent media as these types of facilities install PFAS treatment. So here's kind of what that looks like. If you're going to separate PFAS using media, you've got typically a lead leg pressure vessels where you've got these media loaded in there. The water goes through it with the PFAS. The PFAS sticks to the media, and then at some point, the media is spent and you have to do something. So what happens to the PFAS once the media is spent? That's really the question where we're focusing on here. And then we kind of use some of those project-specific framework questions to guide some of the ways we looked at answers. So some decisions for PFAS separation using media is which media to use, how soon will the media be spent. Those are both pretty well established out there in terms of support for people to help make these decisions. But what happens once the media is spent? I think there's less help here, and also in what is the fate of residuals. So we kind of map this out here. On the left, you see anion exchange resin, and on the right, you see GAC. We didn't look at any of the other media, but I think it would be interesting to do that in the future. So you've got your media in place in tanks. That's kind of the first row. When you remove the PFAS from the tanks, you can either replace the media physically, in which case you have spent media, or you can regenerate it in place, in which case you have spent solvent. And then we get to kind of managing the PFAS residuals. And I'm going to kind of just briefly come back to this PFAS fate and destruction scale, which I think is relevant here. So I've got PFAS disposal and destruction options here on the bottom now, and they're kind of in order of that PFAS destruction scale. I'll talk about these all a little bit more in a sec. The other thing that we wanted to layer on here is technology readiness, because that's very important for people who are operating a water treatment facility or might want to be putting one of these systems in soon. So these are how the Department of Energy defines technology readiness levels. 1 or 2 is kind of on ideas. 3 to 4 is bench scale. 5 to 6 is pilot scale. And then kind of 7 to 8 to 9 is kind of commercially and financially established. So we've put those TRLs on here as well. The technologies to remove the PFAS from the tanks are generally TRL 9, except for GAC regeneration, which remains a little bit behind on TRL 5. And then we've got the TRL for the different technology or destruction options too. So when you look at these different kind of verticals, what you end up with is about 7 different options here to look at. And we worked with all the vendors to come up with operation and maintenance costs and energy uses from them. So this shows the GAC stuff on the left and the anion exchange stuff on the right. And the y-axis here is cost per pound of dry media. And that's kind of why they looked so different for anion exchange and GAC. Usually you use a lot less of anion exchange resin. So when you look at Cost per volume, these are going to be more similar, but the reason we did it in cost per pound of dry media is because then we didn't have to make any assumptions on the water quality or the change out rate. So any facility looking at this could take their estimated media use rates, multiply it by these costs per pound of dry media, and come up with like a range of costs. And you can see by color, these are broken down by the different phases of that media management. So the blue is new media makeup. You can see that's the bulk of it. Media is pretty expensive. The red is the destruction. So GAC incineration fees are also pretty high these days, as well as thermal activation fees. Solvent regeneration costs, those are kind of still being established for some of them. And then transportation is pretty minimal for all of these. The energy use estimates are kind of look relatively similar, again, dominated by the energy needed to make new media. So both cost and energy use, you're going to see a lot of savings if you can reuse the media, either through thermal reactivation or through on-site regeneration. So I want to just talk briefly about some of those regeneration options. So this is regenerable ion exchange. It is at a TRL 9. There's industrial wastewater applications at over 1 mgd. And it has a pretty high concentration factor. And then the residuals, you can there's a couple different destruction options. This GAC regeneration one is technology readiness level of 4 or 5. There's ongoing pilot activity here with some larger changeouts, hopefully later this year. But one of the nice things about this is this could potentially be retrofitted into an existing drinking water plant that has GAC there. And you just need to retrofit it with equipment to manage this solvent regeneration on site. And then either you could buy a system to regenerate it on site, which is that bottom part, or you could have this mobile regenerant truck come and do the regeneration for you, which is the top part here. So those are kind of developing and are getting to be options here. I want to talk through a little bit of kind of how this decision making comes into play. So I've got 2 graphs that I'm going to show here, and these show some of the project priorities you might see. So this one shows kind of larger to smaller facility on the x-axis, and then the y-axis shows PFAS concentration, and which is related to media use rate. So here we've kind of mapped those different options on there. So if you've got a large facility with high media use rate, regenerable ion exchange with liquid disposal makes a lot of sense. If you've got a small facility with lower media use rate, you might want to just get GAC with change out in thermal disposal or kind of one-time use GAC. And similarly, thinking about organizational priorities. So some organizations might only want demonstrated technologies. That's where we're at for drinking water treatment. Or you might have an organization where you could get by with an innovative, more early technology. And then there's different priorities in terms of whether people want low O&M costs versus low capital costs. So we've mapped those on here as well. I'm not going to talk through all of this, but this is all in the paper that was published recently in Water Environment Research. So hoping that this is useful to folks planning these types of systems. So conclusions from some of my recent work: general environmental remediation of PFAS is not an option. We need to be prioritizing source control and remediation of high concentration and high risk applications. We should be thinking systematically about technology combinations. Most systems are going to require multiple technologies and a treatment train, and you need to be thinking about kind of your goals and what you're trying to do before you start picking technologies. And then we should have a project-centric approach to drive decision-making. And these are those 5 questions I went through. What is your project goal? What final PFAS fate are you targeting? What phase are you targeting? And which PFAS? And what else is in there? So my asks for you folks listening, if you're a researcher or a technology company working in the PFAS space, please connect. If you want help connecting, I'm happy to make introductions or help connect people. But there's so much good work being done in research in terms of these technologies to remediate PFAS. And there's so much good work being done in companies and startups that are developing and scaling up these technologies. And there needs to be more discussion and collaboration here. I think we could be making a lot more progress if there was more, researchers collaborating with these technology companies to try to figure out what are the problems that they're seeing, and technology companies collaborating with researchers to help them answer some of those challenging questions. I've just listed some of the technology companies here in the PFAS space, but again, if you want to help making these connections, I'm happy to talk to you about it. My other ask here is to think big picture early. So if you're working on projects, what are your project specific constraints? What's the final fate of PFAS you're looking at? If you're working on technologies, like what are the potential applications for the technologies? What are the affordability of those technologies? So think about those and be talking to people about those. So that's the part where I talked about the stuff that I've done recently. I just want to touch briefly on some other interesting questions I'm working on. I'm kind of an enthusiast, so I usually am working on way too many things at once, but I think all of these are interesting. So hopefully they're interesting to you too. One question here is treating PFAS in wastewater effluent feasible? There are very few places that have limits in their municipal wastewater effluent, and most of them are managing them by doing industrial pretreatment. We do have the technology to remove PFAS from wastewater effluent, but can we afford it, and will it do other environmental harm? These are the questions we're trying to answer. So we had a paper come out last year in Water Environment Research, also open source. This was a collaboration with folks at Bar Engineering and the Minnesota Pollution Control Agency. And we looked at Minnesota as a case study and tried to figure out, would this be affordable if we were treating PFAS in wastewater? This graph shows the flow to the wastewater facilities in bins, and then the percent cost for the community as a percent of the median household income. And we found that only 230 of 232 plants analyzed, the vast majority of them would exceed the affordability guidance of 2% of median household income. And that's an EPA guidance. EPA thinks that communities should not be spending more than 2% of their median household income on water and wastewater treatment. So you can see here that if you've got a very small WRF, that community could be spending 20 to 30% of the community's median income on wastewater treatment for PFAS if you wanted to do this. This isn't general wastewater treatment. This is just removing PFAS from the wastewater. And so that seems like too much, considering the health benefits you would get from treating it in wastewater. And so this is meant to be a tool for people developing policies and for wastewater plants kind of thinking forward. So to support that, we developed these cost curves. So we've got flow in to a wastewater plant, and then the estimated capital costs for some different technologies. And then we've got a manuscript in preparation right now. This is also in collaboration with Anderson Ellis at the Colorado School of Mines, but that is to make similar curves for life cycle assessment outcomes. So things like greenhouse gas emissions, ecotoxicity, carcinogenics, kind of if you've got different flows of wastewater treatment plants and you're doing this type of treatment, how much greenhouse gas impacts would you see? And we're seeing that adding PFAS treatment to wastewater plants could double or triple greenhouse gas emissions from wastewater plants in Minnesota and elsewhere. Okay, another question is kind of how much does broad remediation cost? I talked about this briefly, that it's really not affordable, but last year, about a year ago, I was approached by some investigative journalists in Europe, and this was also in collaboration with Hans Peter Arp, who is a professor at the Norwegian Geotechnical Institute. And we're working on a manuscript right now, but the preliminary results are available at the Forever Lobbying Project. If you Google that, you should find it. But we basically estimated how much it would cost to remediate PFAS in Europe. And here's what we looked at. We looked at heavily contaminated soils, landfill leachate, drinking water treatment plants, and then wastewater effluent and sludges. We looked at two different scenarios here. The first is like PFAS that's already out there and just looking at the long chain PFAS. And then for the emerging scenario, we added the wastewater effluent biosolids. We also added looking at ultra short chain PFAS as well. And here are the costs for those two things. This is it looks like it's kind of cut off, but it's actually that low much lower in terms of the legacy versus the emerging costs. You can see the emerging costs, the wastewater effluent is a big part of it, which I just talked about. But then if we look at the drinking water costs, the blue bar on the left is almost invisible, whereas the blue bar on the right is quite a bit bigger. If we are going to target that ultra short chain, the shortest PFAS out there, TFA, the drinking water cost for a region could increase by like a factor of 50. And that's kind of two parts there. The first is that if you're targeting TFA, more utilities have to treat for it. Under current drinking water law with the PFAS that are included, in Germany, they only expect to have about 5% of drinking water utilities would have to treat for PFAS. In the US, it's expected to be something like 15% of drinking water utilities would have to treat for PFAS to meet the MCLs. But if we're treating for TFA, TFA is pretty ubiquitous at pretty high levels. And so we are assuming that basically everyone would have to treat for TFA if there were drinking water restrictions on it. And then removing TFA is more expensive than long chain, as I mentioned a few minutes ago. But those combine to say, like, if you're going to treat TFA versus targeting like PFOA, PFOS types of things, it's going to make the cost of removing them 50 times more. Another question I find really interesting is what are options for biosolids? There's a lot of discussion and media these days about biosolids, PFAS and biosolids potentially contaminating land and food and other things. So this map on the right shows biosolids land application in Minnesota. And on the left, I'm trying to visualize like what are the cost, logistics, and environmental impacts of other alternatives. So there's a lot of people who are like, oh, we shouldn't land apply biosolids, but I don't think anyone's really characterized very well what we could do instead, and would it be better? So I'm working with some students to do that. What we're doing is we're doing a case study for Minnesota. We're planning out some scenarios of like where we could have centralized facilities to treat them, because we wouldn't be able to treat PFAS at every single wharf. Doing conceptual design of that treatment, estimating the costs of those treatments, environmental impacts, and also including fertilizer needs. So if we're not land applying biosolids to a lot of land, then you would have to add additional fertilizers. And the backstory here is land application is the most common method to dispose of or to manage biosolids in the country. But in Minnesota, it's something like 0.1% of land has ever seen biosolids. So it's not like most of the land receives biosolids. It's just most of the biosolids gets disposed of this way. So looking at that, this is kind of the map of what I think would need to be considered to understand all of those logistics. I'm not going to walk through all the details here, but what you should know is this green box is what most people are thinking at when they're thinking about biosolids treatment. They're like, well, how would we remove the PFAS from the biosolids? So that is important. And there's a lot of great work being done here, but I don't think anyone is looking at this whole big picture. Like, how would those wharfs dewater it before they go? Would they keep their anaerobic digestion or not? How would they blend it together and dewater it on site? What happens to the residuals? What happens with the fertilizer makeup? How was the transportation network going? So we're trying to think through some of this and kind of hopefully get some progress here in the industry to think more broadly about this. The last thing I want to talk about is I've been collaborating with some faculty in our College of Business here at St. Thomas, and we're trying to figure out if we can help companies phase out PFAS. A lot of the work I've done it really highlights the importance of source control and using less PFAS. So this Amara's Law is the use restriction in Minnesota, where PFAS is not allowed in 11 different categories of products now and is not going to be allowed in other products by 2032 unless there's a specific exemption. And so we're trying to kind of talk about how that impacts the PFAS in the environment in Minnesota, and if we can develop some guidelines and resources for companies to actually figure out how to identify PFAS, how to phase it out, and how to plan for the future. So that's kind of what's going on now. Thank you for listening. I appreciate y'all being here, and I'm very interested to hear what sorts of questions you all have.
Great, thank you so much. Yeah, so this is the Q&A portion. Really great presentation. I know Allie will be able to answer all of your questions. So we do have a couple already in the queue, but feel free to keep sending them in either in the chat or in the Q&A. The first question is from Federico. He is asking, what is the likelihood that treatment technologies will generate PFAS precursors and short chain PFAS?
Yeah, this is a very good question. I think it depends on how you define precursors. I think typically the treatment technologies are going to oxidize precursors or turn PFAS into like end product PFAS rather than into precursors, just by how we define precursors. But I think there's potential for a lot of these treatment systems to form short chain and ultra short chain PFAS. I saw there was a study that recently came out looking at incineration and formation of TFA in incineration and how that was. I didn't look at the method specifically, but I think the concern about forming short chain and ultra short chain PFAS from some of these treatment technologies is very real. Some of the treatment technologies are working on trying to do analytical that's aimed at closing the fluorine balance, which is kind of like what you need to do to show full defluorination. So there's progress being made here, but it is kind of challenging.
Great. Next, Aaron asks, do the different classes of PFAS have different health impacts, or are they all relatively the same?
Yes, very different. This is also a good question. If there's 250 PFAS that we need to be worried about, we need to understand the health of all the different ones. There are some PFAS, there's a limited number of PFAS for which we have experimental evidence or epidemiological kind of correlations for health effects. But for some of the other PFAS, people are working on kind of chemi-informatics, where they're trying to group PFAS into like compounds and estimate their toxicity from the toxicity of other similar compounds. So there's a lot of work being done in this space too.
Great. Uh, and then Len asks, how closely have you looked at microbial digestion of PFAS?
Yeah, I love this question too because I love microbes and I'm like a huge microbe nerd. Um, Unfortunately, the thermodynamics kind of limit the effectiveness of microbial transformations. There are a lot of companies and people out there that are out there trying to defluorinate PFAS with microbes. I have not seen any evidence that that is possible yet. There's certainly places where microbes can take one PFAS and make it into another PFAS, sometimes a less harmful PFAS, which might be useful, but I have not seen any evidence that it would be possible to, example, take PFOA and turn it into something that is not a PFAS compound. I think just the thermodynamics of that in terms of the energy needed and the fluorine toxicity and all stuff like that, I'm not sure that it's possible. That doesn't mean we shouldn't keep trying to figure out if it is, but I'm not sure that it is.
Great. And then Judith asks, is TFA formed through atmospheric transformation of longer chain PFAS?
Yeah, a lot of TFA formation is presumed to happen in the atmosphere. It's not, I don't think it's usually from like long chain PFAS because long chain PFAS don't get into the atmosphere very often, but it is formed from in the atmosphere from degradation of a lot of refrigerants. So this is kind of a complicated backstory, but when the Montreal Protocol went into effect and banned chlorofluorocarbons to save the ozone layer, that was really great to have an ozone layer. But the replacements for that often were hydrofluorocarbons, which degrade into TFA when they get into the atmosphere. So yeah, TFA is a common degradation product of refrigerants and also from pesticides.
Cool. Okay, so June Hong asks, could you please comment on the importance of PFAS separation in the context of water reuse?
This is a really good question, and I think I haven't looked that much into PFAS and water reuse. I know it is a concern, and I think that um, especially, reusing wastewater for treatment is essential for a circular water economy, but trying to figure out how to mitigate PFAS in there. I think it's, equally relevant for recycling other streams like plastics and glasses and, other stuff. Um, so I think, if you wanted to do water reuse and have a separation step, if you've got, an RO system or a GA system in your water reuse treatment trains, you might be getting some of that already, but you might need to alter the operations of it to try to make sure you're getting PFAS out, or you might need to change the design of that a little bit.
Hmm. And then we have a question about could you maybe talk about how public opinion and community interests could influence PFAS remediation or treatment or use in the broader context?
Yeah, I thank you very much for this question. And I think this is one of the biggest challenges with PFAS. It's captured a lot of attention, and I think the answer, as with most things, the answer is often something in the middle. I think there are people who are worried about PFAS everywhere and they're very anxious about it, and maybe they don't actually have that much risk. I think there are certain communities in the US and elsewhere where there's been a lot of PFAS contamination and a lot of people negatively affected by it, which is very much a real thing. But those are not most communities. Most communities have very little health impact from PFAS. So I think kind of a nuanced understanding. I think risk communication to the general public is really challenging and something that professionals need to get a lot better at. But there's also people out there who are like, PFAS is not a problem. And as I highlighted earlier, the persistence is a big problem because it is irreversible in many ways, is that we put PFAS out there and we don't, we understand some stuff about their toxicity and their buildup. But if you keep making it and putting out there and it never goes away, it's going to be a problem at some point. It's, everything is toxic at some point. And so if we don't do something about it and make and emit less of it, it might not be an immediate problem for people today, but it is certainly going to be a problem in the future. And I would really like for people to still live here in 100 years, 200 years. And so I think we need to be thinking about that too. And I think a lot of the risk assessment frameworks and policies that we have don't necessarily account for persistence super well. I think Europe is doing some good work on integrating persistence into some of those frameworks, but I don't think the US is really thinking about that very much.
Hmm. And then kind of like a follow-up on that, like speaking to the general public, what do you think are like the key education points or just like key pieces of knowledge that you think the general public should have around PFAS?
Yeah, I think number one is that most of your PFAS is not from your drinking water. Most of your PFAS is from products that we use in our houses and in food and stuff. So I think people need to think more broadly if they're worried about PFAS and understand that the way to reduce exposure is through restrictions in products. And then I think the second most important thing is kind of what I highlighted at the beginning of my presentation is like we cannot manage environmental PFAS and human exposure risks by remediating PFAS. We need to be going upstream to do use restrictions and emissions reduction to manage both health for current people and for future people.
Mhm. Great. Um, Cool. So we'll just go down the list. We have another question about does it make practical sense to focus on core PFAS rather than short chain PFAS when evaluating and treating sites in areas like Canada, where they're just starting to look at PFAS closely and considering regulations around that?
Yeah, this is a good question. And, I presented the cost to remediate TFA. I do not think we should try to remediate TFA everywhere. I think we should try to make less of it and remediate it in places where it seems like it's a huge problem. In terms of, I think it is pretty well established that PFOA and PFOS are more toxic than some of the short chain ones. And so I think focusing on them does make sense. And from a practical standpoint, if we're thinking about remediation, if you're monitoring for like 50 different PFAS compounds, it can be really complicated to do that. But if you're monitoring for a smaller amount, you're probably removing other ones as well. So I think, it depends on the site. If there's a lot of a specific short chain at a site, you might need to focus on short chains. But if it's mostly like legacy contamination, it's dominated by PFOA and PFOS, I think it's probably okay to focus on those if we think that those are most of their health risks.
Gotcha. Great. And then probably only have time for one more question, so I'm just gonna pick one. We do have a couple unanswered, but maybe there's some follow-up opportunities there. What are the alternative monitoring technologies to validate the existing or emerging treatment technologies?
Yeah, this is kind of gets back to the fluorine mass balance that I talked about some vendors trying to achieve. One vendor that we work with, Aquaga, has been doing some good work in this, and they've got some papers on looking at fluorine mass balance. You could take a look at those and kind of see some of the methods. But you can measure kind of like total organic fluorine using something called combustion ion chromatography. I'm terrible at analytical chemistry, so this is all from me learning from people smarter than me, but combustion ion chromatography. There's also more developing methods. There's a particle-induced gamma emission, which is abbreviated as PIGE, P-I-G-E. And there's also some fluorine nuclear magnetic resonance, FNMR. Those are all technologies kind of evaluating and trying to characterize some of that total organic fluorine that's not just limited to the specific compounds.
Gotcha. Okay. I think that's all the time we have for questions so far. I do want to hand it off to Melissa, who's going to give some closing remarks.
Yeah, just really want to say thank you to our speaker, Dr. Ali Ling, and thanks to all of you here for joining today. We have several more seminars planned every month And so please go take a look, register. Haley just dropped a link in the chat here. Next month's is on October 1st, where we will have Dr. Lee joining us to talk about water membrane design and innovation. So again, these sessions are being recorded, so they will be shared out as well. But thank you again for coming, and tell all your friends. Thanks, everyone.